Hey, what's up, guys? This is Cheng here. So today, let's take a look at this weekly contest, the last hard problem, which is number 1585. Check if string is transformable with substring sort operations. This is a hard problem. Yeah, I think it's really tricky problem. It is hard. I mean, even though the coding part is not that difficult, but the intuition is not that easy. Okay. So, okay, let's take a look. Basically, you're given like two strings, a source and target, okay? And you want to transform string source into the string target by using the following operations. You can use as many times as you want. Basically, you can simply choose any of the sub array, and then you can like sort. You can sort them basically. You can sort the any subarrays, okay? And return true if it is possible to transform string S into the target into the string T, otherwise return false. Okay, so a few examples here. I mean, for example, this one, right? So the solution it gives you is the example is like basically first like sort 5 3 to 3 5, and then we sort uh 8 3 4 to 3 4 8, and then we got the answer. That's why we return true here. And for this one, it gives you another example here. Basically, there's no way we can transform the S into T uh, because the 3 4 cannot be transformed to 4 3. Okay. Okay. So and the S length is like 10 to the power of 5, which means you can only solve this problem by using either a linear time or n log n. Okay. Oh, and S and T only contains digits from 0 to 9. Okay. So that's the constraint here. I mean, so at the first glance, right? I mean, I think for most people, they will try to follow what the problem is asking us to do, basically. So we will be trying to sort like this, sort the arrays, right? Basically, I think the first approach will always be like what? Uh, we find the target here. We find the target three, the first one. Okay, so I think we should always start from the first one, and we find three here, and then okay, we'll try to see, okay, what's the index, what's the position in S, okay, and then can we sort that? Can we reverse this three to the current position, okay? And then if we can, right? So in this case, let's say we sort three. Now it's going to be 3, 4, 5, 8, 2. Okay. Now the 3 is at the current position here. Okay. Now we will look at 4 here. Can we put 4 here, and then 8, and then 5 or 2, etc., etc., right? I mean, this one, the first approach intuition is more like a pancake sorting. If you guys still remember that, basically we just sort a subarray, and then we try to make this source equals to target. But the problem of doing this is like the overhead is too high, you know. And another thing is that, I mean, since every time we'll sort everything. Let's say, for example, let's say we have a very long list. We have a very long list here, a source and target. Okay, and let's say the first element in the target is 2, and it happens that 2 is the last one. Happens to the 2 is the last one in the source ticket, in the source string. So what we're going to basically try to flip, make sure this 2 is the smallest. Basically, we have to make sure 2 is the smallest number, right? Uh, among all the previously numbers. Okay, that's how we can make sure, right? We after the sortings, 2 can be placed at our current position. Then in order to do that, we have to basically loop through everything, all the numbers in front of it, right? And then I mean, even though we can do it because the I think the constraint says we can there's only one 0 to 9 like numbers, so that we don't have to let's say there's like uh, a one 10,000 numbers here. I mean, basically we don't have to loop through 10,000 numbers here. Instead, we can what we can do, we can like basically create like a hash table or like or whatever, or list of lists. Basically, we store each number's index, right? In that hash table or a list of list. Then we just compare. Uh, since this is two here, so there are only two smaller numbers before two, which is zero and one. Okay, so we just check if among zero and one, if there's any index that is smaller than two, then we know okay, we cannot sort, we cannot move this two to the front. Okay. I mean, actually, remember this. So basically, in our second solutions, we'll also utilize this kind of idea here. But okay, so let's say we find that we can sort, and then what do? We sort everything. Okay, we're gonna sort the target as. Are we going to do a as sort here? Right? We do a sort, and then the sort will be changed, and then we're moving to the second one. Okay, now we're comparing the second as here. Now two is here, okay, and now we have like a totally different sorted array here, okay. So that will be a lot of overheads, basically, and it's not a good solution because we are actually, by sorting the two here, we are breaking the relatively positions, right, uh, between among all the previously numbers, which we don't need to do, right? For example, in this case, I mean, uh, let's say we have like how can I say that? Let's say 8, 4, 5, 2. Okay, and let's say this is S. Okay, and the target is what? The target is 2, 8, 4, 5. Okay, this is pretty easy, right? I mean, let's say if that's the case, right? I mean, if this is the one, I mean, we move to the beginning, right? But let's say we do a sort, right? And there's gonna be a 2, 4, 5, 8. Okay. Now we have 2, 4, 5, 8, but our target is this, so we have to keep doing the sortings, which will be like too much like overhead. Actually, the correct solution for this problem is that while moving the two to its desired locations, we should maintain the relative positions of the remaining numbers. So how we're doing that? Basically, every time we're only doing like a swap with its like previously numbers. Basically, we swap 2 to 8 here. So 2 will become to here, and then will become to here, will become to here. So this is exactly like the bubble sorting, right? So the way it's because we can do unlimited times of sortings. Okay, basically we only sort these two numbers. Now this after sorting 5 2, it becomes 2 5, and then we sort this is 2, and it's becoming 2 and 4, and then we sort this one becoming 2 and 8. And I think you guys have already discovered you can only keep doing the sortings until you reach a number that is smaller than him. Okay, let's say we have 8 0 4 5 2. Basically, it means that you can only uh, bubble the twos until here. So once two is here and you have a zero in front of him, then there's no way you can keep doing the sortings. Okay, and that's the one other intuition. And okay, come back to this problem, right? How can we do that? basically, we just okay, I'm going to use this one as an example here. Okay, so we have a 8, 4, 5, 3, 2, and the second one is a 3, 4. The target is this one. Okay, and so first we're gonna like pre-process the source string, and we're gonna store all the indexes for each number so that it can be used later on. And then we will be starting from the target string here, one by one. We start from the first one. Okay. And the intuition is we always try to uh, bubble the 3 to the front of to the very left. Okay. So why is that? Okay, because let's say that we are at 3 here, right? We're at 3 here, and then we're trying to bubble 3 to the very left. Okay, and then so how can we make sure we can bubble 3 up to the very left? Like I said, we just need to make sure for all there's no basically there's no numbers which is smaller than 3. In this case, it's 0, 1, 2, right? Appears on the left side of 3, right? It's pretty straightforward. If there's any like 0, 1, 2, 3 on the left side, then we cannot bubble 3 to the very left. Okay, so in this case, we can. Okay, and so after the bubble up, right? So we have like a 3. Then we have like 3, 8, 4, 3, 8, 4, 5, 2. Okay, and after that, basically we're gonna remove these two numbers from both the source and target. Basically we're done. By removing, I mean I'm going to remove those indexes. These indexes from the pre-processed like index hash table, so that we know okay 3 is done, and this is also done, right? So now the target becomes to 4 here. So which means now we're processing 4 here. Okay. Now the 4 becomes to the the very left. Okay. Now the problem is that like can we move 4 to the very left? Because remember, so here at this moment, right, there's no more 3 here. So that's and since we're at this 4, and since when we're processing the target here, we are like processing from left to right. So this one is as if every time we're always at the leftmost side of the target string here. That's why we can think of this. We are always trying to move this number, right, from the source, from the source string all the way to the left to be able to match with with this position here. Okay. So now can we move 4 to the very left? Yes, we can, right? Because there's no 0, 1, 2, 3 on the left side. Even we have a 3 here, but since we have already matched 3 already, that's why the index of the 3 had already been removed from our array or hash table. So that's why when we check the 4 here, we didn't see any 0, 1, 2, 3 here. That's why we can simply move like the 3, sorry, the 4 here. Okay, now the 4 is done. Okay, now it's the time for 8. Okay, same thing, right? Now, do we have like 0, 1, 2, 3, 4, 7? No, right? Because the 4 and 3 they're all gone. So now 8 is gone. Same thing for 5. Is 5 there? Okay, can we move 5 to the very beginning of the array here? Yes. Now 5 is gone. 2 is gone. That's why we have a true here. So another example, let's say 1, 2, 3, 4, 5, and 1, 2, 4, 3, 5. Okay, source and target. Okay, same thing. So for 1, pretty straightforward, right? Because at this moment, there's no 0 on the left side. on the left side of 1 here. So 1 is gone. Same thing, 2 is gone. Okay. So now this is the S and T here. Okay. And at this moment, we're trying to move 4 to the left side of to the left, the very left of the S, so that this 4 can match with the target. But since, as you guys can see, there's a 3 here in front of 4, which means we cannot move 4 to the very left of the current S here. That's why we have a false here. Okay, cool. So I think that's pretty much the intuition of this problem. And as long as you can figure out the nature of this problem is just trying to move each number to the very left of the updated string, right? So the way we're doing it, the way and when it convert to the coding, it means that do we have any unprocessed number, right, which is smaller than 4, that's on the left side of 4. If there is, then it means that we cannot move this one to the very beginning so that it can can match our current target string here. Cool. Uh, all right, so let's start coding here. Like I said, let's try to do like n of s here. And like I said, we need to pre-process the indexes, right? So since we only have like from number 0 to 9 here, we can simply do a array for like in range like 10, right? That's the all the numbers we need. And yeah, and since we're going to pop on the left side, uh, let's do a DQ here. We're going to do a DQ since we're going to pop on the left later on. Uh, yeah, okay. Oh, and I think one thing I haven't noticed that, let's say we have duplicated numbers, right? So the reason we're doing a DQ here is because, let's say we have a 2 threes here in the source like string here, and when we're trying to match with the target here, right? Every time we have a target here, and once we find uh, once the target 3 has been matched, okay, has been matched here. Let's say, for example, 3 here. We're going to remove the ones on the we're going to remove the index on the left side first. Basically, every time we try to remove like the index from a source index, we always remove the ones on the very left. So the reason being is that, we do this so that, uh, so that, let's say we have a 3 here, right? We'll be matching the numbers on the left side first, because this one has the better chance of matching the 3 here. Okay, because let's say we have like we have 4 here, right? We have 4 and 1 and 1. So now we have a 3 here, and then we have maybe another 4 here, and then in between we have like how can I think of this? Maybe 2 5 3. How about this? Okay, so let's say we have a 1 4 3 2 5 3, and then when we match the 1 3 4 here, so one is matched. Okay, now let's match 3 here, and basically we're trying to match the ones on the very left. Okay, with 3, it's kind of obvious, right? Because why is that? Because if we're trying to match this 3 here, okay, then it means that they're like Uh, there are like then let's see here. So this is because every time when we try to match the compare the index, we always use the index on the very left one because if we use the index on the later one on the on the right side, then we have a 2 here, but that's not correct because we haven't reached that part yet because we have to match the 3 here because let's say we have 2, 3, 2, 5, 3 here, you know. So when we match 3 here, we always want to match with the very left 3 here so that when we have 4, 2, 5 here and then 2, 5 are gone, and when we match the next 3 here, it's also valid. That's why we have to use the DQ. Basically, every time we finish a mapping, we pop this index out of the DQ here. That's why we do a pop left. Okay, so all right, so that's that, and now let's pre-process the indexes for si uh, in enumerate as we have indexes. That's the what's the number c. Oh, since we are going to compare the smaller numbers here, we need to convert this character into an integer so that we can compare them, right? Dot append I here. Okay. So now since the index is always increasing, right? So that's why we have a DQ, a DQ with the index from smallest to biggest. So now let's do the target. Okay. Uh, we have a target character. Okay. In target uh, target number. Okay. In the int equals convert this one to C. Okay. Target number. So like I said, I mean I think we also need to check one more thing here. Basically, if the target number, if the target number does not have any indexes left, like say for example the example 4 here, when we comparing 2 here, okay, so there isn't even any indexes for 2 left, and then we can simply return false. So that's why we have to check is this one, if not indexes, right? Is target number. Basically, this one is telling us, right? It's checking like if there's no more indexes in the source string to be matched with, then we can simply return false here. Okay. So otherwise, if there is, then we just need to check. Okay, if there's any basically if we can move this card number uh from the updated source string to the very left. So the way we're checking it is this one can only be moved to the very left if there's no smaller number on the left side of this number. Okay, right? So how can we do that? Like I said, since we only have like 0 to 9, to be able to search, we're gonna use like a brute force way of searching all the indexes, which is smaller than this number. So we do a smaller number, okay? In range t, sorry, t number. That's how we search the smaller number for this number. And since we have a hash table, right? We all we need to know is that okay, if the indexes for this smaller number exist and and the smaller number. Okay, so since if there are like more than one like appearances for these smaller numbers, like I said, we always use the ones on the very left because we're trying to move this number to the left side, right? And what? And the indexes of the smaller number, the zero. Okay, this zero means that if there's like more than indexes for the smaller number, we just need to get the very left one. Okay, if this one like is smaller than the indexes of the target number dot zero, right? Like I said, we always all we care is the very left one. Okay, if that's the case, right, we simply return false because we know, okay, we find the smaller number on we find a smaller number for the card number. I mean smaller than the card number on which is on the left side, which means we cannot move the current the t number to the very left. Then we return false. And if if it can be moved to the very left side, then we can simply pop, right? Basically, the way we're popping it is to what we do indexes, right? Number dot pop left, right? So this one means what? It means that like uh, it means that I mean after matching the three here, okay, the three and three here, so we need to remove we need to remove the indexes, right? From the source basically we're removing this number from the source string. Okay. And the way we're removing it, we're removing this number's index from the indexes like a list here. So that later on when another number trying to look for the trying to search the indexes again, it won't see this index or this letters again. Okay, cool. So and then if everything works fine, we can in the end we simply return true here. Cool. I think this should work. All right, so this one is true. Submit. Cool. So it accepted. I mean, and and as for the time and space complexity, right? I mean I think the space is also linear because you know even though we have like only 10 elements, but for each of the elements we could have like many indexes, which is the number of n here, right? And also the basically that's the space complexity, and for the time complexity, I mean this one is like a for loop, so it's on, right? So also linear, like on. This one is also like this is also on. And when it's for inside the loop here, um, I mean, even though we have like a for loop here, but this one is bounded with 10 here, okay, which is like constant, right? So we can also like treat this second one as on. So yeah, basically, you know, and this is like O1 here, and this is also O1 to look for the 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 array here, right? So I mean, space and time complexity, they're both like linear, which is O of n. And yeah, I mean, that's I think that's pretty much it is for this problem. I mean, it's a very tricky problem. It requires you to make a few like tricky observations. Like first one is to you know, sometimes, or I would say most of the times, the way they're describing the examples is always misleading. It basically they're trying to hide the true nature from this of this problem from you. That's why they doing the like the sortings this way, right? So I mean, if you follow this one, probably you end up like in a not in a bad situation, right? So I think the first difficulty for this problem is that you have to be able to figure out why since you can do the sortings as many times as I mean as you want, right? So the the nature, right, of moving three to the desired position is to make sure we can uh, swap, or we can swap the three all the way to the beginning. So when I say swap, which basically since we can only do as ascended ordering, it means that you can only move three to the left when the left one is greater than three. Okay, and we're doing that by also maintaining the orders of the remaining uh, of the all the previously numbers. Yeah, and the second one is that I mean every time once you finish matching one of the numbers, you need to remove that. You need to remove that from the indexes so that I mean the next number will not be using that like the match number as like as the criterion to determine if it can be moved to the very left. And the third one is the only the relative position matters. I mean, let's say for example, like we have 8, 4, 3 here, right? I mean, if you're looking at 3 here, if we have 3 here, okay, so we match 3, I mean we match 4, and then when you are looking at 8 here, I mean, you may be like, okay, the current 8 is at index 2 here, and the source 8 is at index 0. And do I need to worry about that? Okay, right? I mean, it turns out that you don't need to worry about that. Like I said, I mean, after removing matching 3 and 4 here, right? 3, 4, 8, 5, 2. Oh, sorry. After matching 3 and 4, okay, all we need to care is the relative position of the remaining the remaining like the numbers, because uh, the way we are like matching the 3 and the 4 is we're not disrupting all the other numbers relatively position. That's why we can simply ignore the current position of 8 and this 8. Okay, so all we need to care is that can we move the current number from in the source to the left, to the very left from the source string. Okay, cool. I think that's pretty much it is for this problem. I think, oh, sorry, I think I already said that before. Sorry, sorry about repeating myself. I just want to make sure you guys understand this like it's a hard problem clearly. And okay, thank you so much for watching the videos, guys. Stay tuned. I hope you guys like the videos, and see you guys soon. Bye bye.